We will begin, so thank you all for coming, thank you for your patience. As you're probably aware, this room is more used to the somber business of running a physics laboratory than the kind of event we're holding here today. It's my pleasure to introduce you to our Director General, Rolf Hoyer, the spokespersons of the two LHC experiments involved in today's announcement, Fabiola Gianotti for Atlas and Joe Incandela for CMS, our Research Director, Sergio Bertolucci, and Steve Myers, who is our Director for Accelerators and Technology. As you will also be aware, we're also honoured today to have four of the pioneers of the theory of electroweak symmetry breaking with us, Francois Onglet, Peter Higgs, Jerry Guralnick and Carl Hagen with us. They're in the front row here. They will be willing to take your questions during the press conference. We are also live, I believe, in Melbourne, where there are journalists following us there. For people who couldn't be with us today, journalists who couldn't be with us today but who are following us on the webcast, we are looking at Twitter. So if you want to ask a question, tweet it to iChep, #iChep2012, and we'll do our best to answer them. And with that, I will hand over to our Director General, Rolf Hoyer.
Yeah, thank you, James. I don't want to make too many words. I think you have heard the words I used at the end of the seminar. I think there could be worse days in the life of a Director General, I must say. As a short introduction, I'm really pleased with what I saw today. I'm really pleased with all the work which went into, all the dedication, all the people who are now tired and have done a remarkable and marvelous job, as I said, from the accelerator to the experiments to the grid computing. That all has contributed to this success, and I think we have a success today. We have a discovery. We have discovered a new particle, a boson, most probably a Higgs boson, but we have to find out which kind of Higgs boson this is. Does it have the properties which we expect from the standard model? If not, what are its properties and where do they point to? But at least we know now that we can soon close part of the chapter of the standard model. We have now found the last missing cornerstone of it, I think. So I'm really happy, and now we also know which direction to go for the future. But first of all, as I said, it's the beginning of a long journey to investigate all the properties of this interesting particle, because if it has a spin zero, if it is a scalar, it would be the first fundamental scalar which we ever have discovered. We have not yet ever seen a fundamental scalar. And that could give a lot of hints on other questions beyond the standard model. And I think this is very, very important. And this is why everybody is not only excited about the discovery, everybody is also excited about the prospects this discovery opens for us, for the field, and for physics in general. I think that's enough. So you can have now your questions.
Hi, Jeff Brumfield with Nature Magazine. In the press conference, in the seminar just now, you said, as a layman, I think we have it. So what would you have us write today? Have you found the Higgs or what?
Well, I think I just said it. As a layman, I would say we have it. But as a scientist, I have to say, what do we have? We have something, yeah? We have discovered a boson. And now we have to determine what kind of boson it is. That's in the scientist's language, so to speak. Does this answer your question?
Can I ask something? I'll just jump in. It's Ian Sample on the Guardian in London here. Can you tell me how far do you expect to get in finding out more about this particle before you shut down temporarily at the end of this year? What are you going to? How much further do you think you'll get in understanding what this is?
I have an expert to my left.
Okay, so it's quite early. As you know, we're just seeing this thing emerging, and it's difficult. I showed some very early measurements, but we've done some projections and some studies to see, could we tell if it was a scalar, for example, or a pseudoscalar? And we're hoping that with the additional running We might reach the point by the end of the year with the combination of both experiments to sort of separate that sort of information, for example. We also hope to see a lot more information in the various channels and see that those balance out correctly. But to say definitively that it is a standard model Higgs would be very difficult.
Sorry for that. Yes, my question is to Professor Higgs. If you could comment as a layman, as a scientist as well, what is his impressions? Would he say we got it as a layman, and as a scientist, what would he say? Thank you.
I think it's not appropriate for me to answer any detailed questions at this stage. This is an occasion celebrating an experimental achievement, and I simply congratulate the people involved.
Sorry. Hi, this is Celeste Beaver from New Scientist. Why are the masses different, and is that important?
What the experiments observe at the present moment with the data that we have available today, the results are fully compatible within a given experiment and across experiments, because we observe, say, the maximum of the excess between mass of 125.5 and 126.5, which is really at this stage compatible. But of course, as Joe said, it will be very important in the next months first to consolidate within the individual experiment the observation in the various channels. For me, the fundamental thing is to see how the excess and the signal looks in the various final stage, to see how this particle couples to all the other particles, fermions and boson as we call them. And then at some point it will be also very interesting to combine the two experiments, our data, to of course to fully exploit the statistical power of the data sample and the data that the machine has given us. And so at that point we should be able also to give the best parameter of this signal.
So they're close enough to each other that they do complement each other?
Absolutely, absolutely.
I was just going to say that I'm sure you'll see, as we get a little further along, even with this data set, that the masses are completely consistent within uncertainties, because the uncertainties are still large.
Okay, good.
Okay, now the order is him, then you, and then you.
Do I just speak? For the other laymen out there, about 6 billion of them, what does this mean? We've heard that if it is the Higgs, it explains why we have mass. Is that your best shorthand explanation for the rest of us of what this means? And if we didn't have an explanation, and did we really not have an explanation before this of why we had mass?
I think I first have to correct, with all respect, with Peter Higgs and the other theory colleagues here, it's not what gives you the mass. That's different. That's a different mechanism. What this, if it's a Higgs boson, what this Higgs boson would tell us is that there is a certain field out here, everywhere, a certain field through which the fundamental particles, like the quarks, the bosons, get their mass. It's not that you get your mass. How can you imagine that this thing works? Well, you take a large room with journalists, okay? And they are all equally distributed in the room. This is the field which would give mass to elementary particles through the interaction of these particles with the field. Somebody who is completely unknown to the journalists can go through this field, through the journalists, with speed of light. That means that person would have zero mass. The more known you are, the more journalists are clustering around you. That means you get slower, you don't reach the velocity of light, you acquire mass. The better known you are to the journalists, the more massive you are. Okay? You saw this when you were coming in here, yeah? Peter Higgs was pretty heavy. Huh? Okay? Now that doesn't tell you anything about this boson yet. But this field, as the journalists obviously, has an interaction in between itself, and this self-interaction can produce this Higgs boson. How can I imagine that? Imagine I open the door and I whisper a rumor into the room. Then the journalists are curious, they cluster. What did he say? This cluster of journalists is a Higgs boson. That's easy. That's particle physics for laymen without a single equation.
That's very, very good, thank you. But to the extent that I am made of fundamental particles, does this not have any relevance to me?
I think it has a lot of relevance to you, because if that would not exist, I think you would not exist. I think that's in a very short layman term. You agree?
Yes, absolutely.
Okay, I got agreement.
Hamish Johnson from Physics World. Everyone seems to be saying that this discovery has come rather quickly, or perhaps faster than you expected. Does this mean that that you're going to be modifying the program at the LHC in any way? Do you still plan to stop at the end of this year for a considerable amount of time and then go up to 14 TeV?
I don't know if Steve wants to say something, otherwise I can answer the question. We had a meeting yesterday, Steve, Sergio, myself, with some of our department heads, of course taking into account what the experiments expect and what they would like to see. So we have decided to extend this run, but only by 2.5, okay, let's call it 2.5 to 3 months. We are extending it because we will be shut down with the LHC for nearly 2 years, and therefore we really would like to give the experiments as much data as possible to get a bit more out of the discovery now which they have made. We cannot go much beyond these 3 months because we really have to do a lot of maintenance now. A machine which was running 3 years needs some pause.
Adrian Cho, Science Magazine. So before the LHC turned on, the general wisdom was that the thing that would hop out first, if it hopped out at all, would be supersymmetry, and that everything else would take a long time, and that the Higgs would be a hard slog. I mean, clearly it's taken a while. It's 2.5 years worth of data taking, but it seems to have gone relatively expeditiously. So I'm just sort of wondering, has the Higgs search gone faster than you expected?
I mean, before I give the floor to the two, for me, yes.
Indeed it has gone faster because of, first of all, the impressive performance of the accelerator, which has given us a lot of data, already 10 inverse femtobarn in less than 2 years of operation, and but also very fast because the experiments are working extremely well. So putting all these things together, we were able really to discover this particle, if it is a Higgs boson, but have evidence for a signal of something that looks very much like a Higgs boson in a mass region which is quite difficult to explore quite quickly. It's not that we didn't do similar progress in other fields. Of course, we have looked for symmetry, for supersymmetry, we have looked for extra dimension, we have looked for new things, but for the moment we have found nothing. Doesn't mean that there is nothing else. It means that we have to search more and be more patient. But of course, clearly, understanding the feature of this signal, of this new particle, will also give us direction for the future and to understand perhaps where to look and what are the most likely scenarios.
I would add the same. The detectors we built are really a compilation of generations of experience, and we pulled together people from all over the world. Many different accelerators, many different experiments brought all their expertise, and we built together something that has just remarkable efficiency and capability and information quality, and then we set it loose in some sense on lots of young, ingenious kids. And they have they're a little bit older than kids. To me, they feel like kids. But. And they've come up with exceptional ways of using this information, and we're being surprised every day with how much the capabilities are exceeding our expectations. That's one thing. So the Higgs came faster, or whatever this particle will be, Higgs-like. We have to be careful until we've really understood it. But this all came a little bit faster than we expected. And there was an expectation that we might see some indications of supersymmetry early, because there are models of supersymmetry where the signals would be quite strong. But supersymmetry is a very complicated theory overall, and it's not there. I mean, it's not missing just because we haven't seen it. And in fact, the existence of a Higgs-like particle, a fundamental scalar, actually is a very strong motivation for the existence of supersymmetry. And so in some sense, this is reinvigorating our searches, and there are many places where natural models of supersymmetry can exist, and this is one of the big priorities of the rest of this year of running. We're going to try and hunt it down.
Then I saw your hand, James.
Yeah, we have a number of questions from outside that I'll just throw at you all at once and let you deal with them as you wish. One was, does this have any influence on dark matter? The second was, what else does the LHC do apart from Higgs searches? And the third, how many particles were used in this research? How many particles were used in this research?
Okay, I think he can answer the last one.
I did a calculation. You know, we have proton beams crossing, and then we have proton pairs colliding. And you work it out, it's about 500 trillion that we've had. And so I give you a very simple way to think of this in analogy. There's something like, if you represent each of those collisions by a grain of sand, 100 microns across, you'd have enough sand to fill an Olympic-sized swimming pool. And that's how many particle collisions we've been looking at. In the end, the signals we're showing you are some tens or dozens of particles. So, you know, enough sand to cover the tip of your finger. It gives you a sense of how much, how rare these things are. But we used all of our knowledge of all of the standard model particles in all of these searches as well.
What was the second question?
That was the last one.
Yeah,
that was the last one. They were, what's about the rest of the LHC's research program, other than Higgs? And, does this have relevance to dark matter searches?
Fabiola?
For
the rest of the LHC program.
For the rest of the LHC program, as it was said also before, I think it's very important now that we look at this particle in all details without losing the rest of the global picture. That is, we should not now focus only on these things, because there are a huge number of topologies to look for. So we will continue to work very hard to see if there is any new physics. And I mean, this is hopefully not the only discovery of the LHC. So we'll continue to look at in all possible directions, in all possible topologies until the end of this year. Then again, with more potential and more capabilities when the LHC will start again at 13, 14 TeV in 2 years from now. And hopefully we can discover many more things.
I guess Sergio wants also to say a few words on that.
I want also to add one thing, is that when you are doing a thing like LHC, a program like that, you start, you get on the way because you have a number of known unknowns. And Higgs search is one of these known unknowns that we are solving. But of course, and we have plenty of them, so this is part of our program. But of course, the real reason also why you are making it, you're exploring a new region, is for the unknown unknowns. And we have plenty of them. We hope that they're coming, because this is also one of the reasons that we are moving now to a higher energy, because we want just to increase very much the possibility just to look for unknown unknowns.
Yeah.
Okay, I have now 1, 2, 3.
Ishiguro of Yomiuri Shimbun, Japanese newspaper. It's again a layman question. This sigma 5 means in terms of probability, like 99.99997 or something. How do you express it?
How do you?
Because this probability of existence of Higgs boson is expressed by sigma 5. Then if you express in the percentage, like 99.9999 or something, how do you say it?
It's roughly 1 in 1 million.
3 times 10 to the minus 7.
3 times 10 to the minus 7.
Probability of this.
Yeah.
It's Nick Collinson. It's Nick Collins from the Daily Telegraph. Do you think that Peter Higgs and the other men sitting to my left deserve a Nobel Prize for this?
I don't think that, frankly speaking, I don't think that Hoyer's opinion counts here. And this is a question to the Nobel Prize Committee. I can only say it was a fantastic achievement what they had. And we are not for nothing looking for this famous particle since many, many years, because we took it very serious. But I don't give you any opinion, but it was a great work.
I hate to be the one to ask the fluffy question, seeing sample on The Guardian again. It looked like there was quite a lot of emotion in that auditorium, and I just wondered if you could take us through what the last, say, week, few days has been like, perhaps especially for Fabiola and Joe. And I know you were sort of interrupted by applause and so on. Can you just take us through how your feelings have gone the last few days?
Okay, let me start. It's very difficult to say because the last few days, last weeks have been extremely intense, full of work, emotions. At the same time, we had to be extremely focused, of course, and concentrated in order to be able to analyze very quickly a huge amount of data that were coming out of the LHC. As we said already many times, we have analyzed data recorded until 2 weeks ago. I must say that, I've been in Atlas for many years, and I have the pleasure of being the spokesperson, so I know Atlas quite well, but I was really, really amazed by the dedication, the competence, the skills, the talents of everyone in the experiment. Essentially, a chain which is extremely complicated, that goes from the detector in underground cover all the way through trigger, data acquisition, data calibration, processing, distribution to the worldwide center, and then analysis, and then the plots. This is a very long chain. And not only to work perfectly well, but it was really going, like if it was oil everywhere, no friction. Everybody was doing his work or her work in the best possible way. And amazingly, everybody was really focused and working for the common goal. So it was really a good demonstration of dedication, hard work, high competence, team spirit.
Could you say a little bit about both of you actually, about the reaction? Once you give these results and you see your colleagues' reactions, maybe even just giving them alone is pretty emotional.
Yes, it was overwhelming. It was a magnificent, really magnificent moment to see the reaction of the community. And I felt I felt obviously like I was walking on air, but I think I felt very great for the collaboration because, as Fabiola said, this is an unbelievable amount of work done by a huge number of people. And I don't think people really, it's very hard for us to actually express what's involved. It's so complicated. There are so many pieces of the whole organization that have to work correctly. We cannot have any mistakes in, hundreds of different areas. So we have people working and scrutinizing, and all of the chain has to work, as was said. There's billions of events involved that have to be processed, and they're distributed all over the world, and they all have to come in, and all the files have to be tracked down. But emotionally, it didn't really hit me emotionally until today, because we have to be so focused, and there was so much work to do and so many people to work with, and I'm just super proud of my collaboration for what they've done.
Could I jump in with a question?
Hello.
Sorry.
Can I go? NHK Mitamura. I have a question to Dr. Hoyer. One of the reasons you could get this result, achievement today, is because CERN has put two international research groups, CMS and Atlas, and they have done their research separately. And sometimes they have competed with each other. So this is one of the reasons to come achieve here. You think so?
Yes.
Can you explain more about that?
Well, I think we can go even one step further. It all starts with the international collaboration centered here at CERN on the accelerator. Yeah? I mean, don't forget that this accelerator is running extremely well. Okay, I can only give you now my opinion, and here it counts from time to time. It was better than I expected for the accelerator. And then for the experiments, again, fantastic collaboration, but also competition inside the experiments. You should not forget that also inside the experiments, people are collaborating and competing at the same time. So it's co-opetition, okay? Co-opetition, yeah, this is the word, yeah. Because everybody knows that things can only come out once you collaborate, but at the same time you compete, and therefore there's already a lot of scrutiny inside the experiments. And then I'm very lucky to have two equally performing experiments and collaborations side and side, competing but also collaborating. And the fact that they have not yet combined their results today is that we didn't have enough time. We should have shifted the Melbourne conference by 2 weeks or 3 weeks or 4 weeks, but that was not possible. No, so you have to stay tuned until they at some stage combine their results. Whatever combination you get beforehand is unauthorized and is certainly not valid, because you have to take into account the different correlations. Yeah? One has to be very careful. So all this together, and not to forget, oh, I nearly forgot it, not to forget is the huge effort in the computing. Without the worldwide computing, the grid computing, this result today would not have been possible either. Again, all these pillars are absolutely needed and essential.
Tom Clark here from Channel 4 News with a question for Professor Hauer. Hello. I'm trying to get an idea of how similar the particle that you've now discovered is to the one described by Peter Higgs and his colleagues sitting right next to me.
Oh, I think that's a bit premature. I think we can only say whatever we see, but is consistent with a Higgs boson as it is needed for the standard model. However, there can be subtleties, and don't forget, we still need to take a lot of more data. That means a lot of more statistics. I mean, you can take this picture. You suddenly far away. You see somebody. You think you know that person, yeah? It's your best friend. But you have to check, is it your best friend or is it your best friend's twin? For this person has to come closer, closer, closer. You can compare this with, we take data more and more and more, and then we can compare the shape. And then we finally see, is it that one or the other one? So ask me in 3-4 years.
I look forward to it.
No, I had now, sorry, I lost. I had the lady, and I had somebody else. Yeah, here, then here, and in between you, okay. Or I can only count with one hand.
My question is, which are the main private companies that built the instrument for the two experiments? And in particular, I'm interested to Italian companies. And the other question is, which do you think is the return on investment they will have for this success? No, can
but we restrict it to 3 Italian companies.
We don't even talk about Italian companies. I think that, 1/3 of the magnets of the LHC have been built by Ansaldo, Italy. And 1/3 was built by a French company, Jacques Alstom, and 1/3 by a German company. So a remarkable example of European collaboration with a little spread. And so in a sense, the return, this company, the Italian one as well as the other, they had it even before this success. They will have more. Because they made a study, it was done a study at the European level, and the return on investment in this case, besides the fact that we paid them, so they had immediate return, is essentially that for every single euro they invested in R&D, they got coming back of about 3.5 times as much. So it's a pretty good return.
But maybe one should add at that point also that whatever company is working with CERN or with the experiments, this company has to work at the forefront of technologies. Yeah, because sometimes these guys are asking the impossible. Okay? Then we have the engineers which bring them back down on Earth, and then the companies will produce it. And the main thing is that these companies also learn a lot in these new technologies, and this is a reference for them. And that's a very big issue for the companies to have this reference, to have worked at the forefront of these technologies. I think that one should also keep in mind. Okay, let's add one.
I was just going to add one example, which is that when we first, 20 years ago, started thinking about the LHC in this high-intensity beam environment, we did not have silicon detectors that could withstand, these are what we use in our tracking systems, we did not have silicon detectors that could withstand that kind of radiation. And so there was a 10-year program to actually develop very radiation-hard electronics. And there are many things like this where we will go into a program with a goal for the physics and not necessarily have the technology a priori. We have to develop it. And we did that with many different companies, and I think there's been many benefits to those companies around the world.
Thanks. John Halpern, Associated Press. Will you follow this up with a formal announcement at some point that you have not just found a Higgs-like boson, but you have found the Higgs boson? And if so, when might that be?
Well, I think you have to define for me what is the Higgs boson. If you mean the standard model Higgs boson, then we can answer that question at some stage, but that will take time because, as I said, you have to investigate the properties. Because take supersymmetry, and now I'm looking on my theory colleagues that I don't talk wrongly. Supersymmetry requires a low-mass Higgs boson, and we have a low-mass Higgs boson. But it requires 4 more, at least in the smallest extension of the standard model, 4 more Higgs bosons. And one of them could also be, again, pretty low mass, and these low mass Higgs bosons could have slightly different properties compared to the standard model Higgs boson. And this we have to find out. And therefore, it's difficult to say. I said here 3-4 years or something like this, minimum. You want? I can say something.
Well, I think we have, as I said also this morning, I think we have to be a bit patient. We need to do the needed scrutiny work to understand well with what we have seen. And, you know, we don't know. It's the nice thing of research is that you don't know how quickly you can get some goal and what you are looking for something, and if what you find is exactly what we were looking for. Sometimes the answer is totally different, okay? So now we observe something, we see a signal. We think it is very close to what we expect from what we know, the Higgs or the standard model Higgs, but we don't know the detail. We will have to scrutinize this signal, and then let's see. It can take 1 year, it can take 4 years, it can be a long, long path, because in the meantime we find something else, and this something else will contribute to the understanding of the global picture. So the picture may be much more complicated than what we've seen today. I hope it will be much more complicated than what we've seen today.
Let me just add to that in a simple way, and maybe this will help. At least this is sort of how I look at things. This boson is a very profound thing that we found. Okay, this is not like other ordinary particles. It really is. We're reaching into the fabric of the universe at a level we've never done before. This is telling us something. It's a key to the structure of the universe. It could be the final point in the standard model, but we know at some level we're pretty sure that the standard model is not the full picture. So we've kind of completed one story, one part of the story, if you like, and we're on the frontier now. We're on the edge of a new exploration. And this could open up, maybe we see nothing extraordinary, and we understand that maybe this is the only part of the story that's left, or maybe we open up a whole new realm of discovery. But we're way out on the edge of understanding. We don't know. This is exploration.
As I said, it will be the first fundamental scalar. This is important. This is exactly that point. Yeah? This opens a lot of possibilities. Next question here for
Chris Wickham from Reuters. I suspect the most exciting prospect for you as scientists is to discover that the particle that you've found actually confounds the standard model. But all of the range of options are, of course, terribly exciting. But for you personally, which is it? You know, what would be the most exciting thing? Confirmation of the standard model? It's a Higgs, but it's slightly more exotic. Or, oh my God, the standard model, and with apologies to Peter Higgs, has to be completely rewritten.
Okay, so first of all, I don't think the standard model has to be completely rewritten. The standard model is not complete, so we have to complete. We know that the pieces of the standard model we have tested until now works extremely well. So, and we know at the same time it's not the ultimate theory of particle physics. Of course, the dream is to find the ultimate theory which explains everything, and of course we are very much far away from that. So, I don't think that the standard model is wrong. The standard model is simply not complete because it cannot explain, it cannot answer many fundamental questions. One is the question of the particle, the origin of the particle masses. There are many others, like dark matter, etc., etc. So, concerning my personal feeling, I would be delighted if this new state is a Higgs boson, but perhaps not the standard model Higgs boson, because this will be extremely, I'm sorry, but because this will open the road to something else. But of course, even if it is a standard model Higgs boson, there we know that being so light is something that is a bit uncomfortable for the standard model. So it's perhaps already an indication of physics beyond the standard model. And there are many other subtleties that we have to understand, or we have to, in some sense, accommodate, like the masses of the fermions are not completely explained, etc. So it's very intriguing. I think it's going to be a very interesting time.
I think Fabiola said it very well. Let me just say that as an experimentalist, when we work, we make we have no bias in what we're seeing. We really want to observe nature. So the best guidance that we had was the Higgs theory, if you like, and the theory of electroweak symmetry breaking, and that led us to look for this particle. To explain many of the problems associated with it, there are many different models that we've been studying. But we have as experimentalists, we have no prejudgment of nature, obviously. We're happy to see what nature is. But also as an experimentalist, and just echoing what Fabiola said, we know that the story is not complete. There is dark matter in the universe. There are many questions we cannot solve right now, we cannot answer. It's a rather profound thing that we could maybe answer the question someday of where does our substance come from, where does mass come from. But there are many questions we cannot answer. And so, if the Higgs, or whatever this particle is, whatever kind of Higgs it is, if it is not quite like the standard model Higgs, and we can actually establish that, that will act as a portal in some sense. It will act as a guide that I'm sure the theoretical community can use to profit to helping us to figure out what to do next and guiding our programs. So the more complicated and more bizarre it may turn out to be, in some sense helps us more, but as Fabiola said, let me say, even the mass at the level that it's at is very interesting now.
In a nutshell, for me, I'm just excited that we have a discovery. Okay? This is fantastic.
Paul Rincon from BBC News. I just wanted to, a slight variation on the theme that you've just discussed. Some of the parameters or the channels seem to be showing ranges that are outside the standard model at the moment. I think the gamma is slightly high. What do people think about that? Are those expected to get in line eventually, or do you think they're perhaps intriguing?
As an experimentalist, I have to consider a measurement and its uncertainty. So it's true, gamma, as you have noticed very well, is almost a factor of 2 in Atlas, at least, larger than what one would expect from the standard model, but with an error which is also very, very large. From a statistical point of view, within the uncertainty is compatible. So we need more data to consolidate and to firm up this observation, if it is really larger or not. Okay, so more data, and then of course cross-check with the other experiments, and combination ultimately will tell us what is the truth. So for the moment, everything is open.
There are no serious inconsistencies. These things, though, are something, of course, we like to watch, and we'll look to see what we get to the end of the year, and if the trends continue, it could become quite interesting, but it's too early to draw any conclusions.
Hi, this is coming back to the whole boson versus Higgs boson, but what would really help me is if this is a new boson rather than a Higgs boson, would it replace the Higgs boson? Does that mean we don't need, it removes the need for the Higgs boson, so it's this, is that right? Or can we not even, do we go back to looking for the Higgs if this is just some other kind of boson?
We need something to give the electroweak symmetry breaking. We need something that generates masses. And as Rolf said, there are many models that are more broad than the standard model at doing that. So this boson is very possibly something that is related to this mechanism. Okay.
And don't forget, also the Higgs boson would be a new boson. Yeah? Because, as I repeat again, we have not yet seen such a particle. Call it Higgs or differently. Doesn't matter. We haven't seen such a particle yet. This is what excites us. Yeah? That's the first time we are really moving into a new part of particle physics where we are soon able to investigate in detail the properties of such, I hope it will turn out that it's a scalar, of such a scalar particle. This is the fundamental new thing, in addition. François, you have to push the large button.
Just about what you just said, how long you expect it will take to confirm that it is a spin 0 and not a spin 2, let's say that it is a scalar? Do you have some idea?
It's hard to tell. I think that we didn't really study in detail how much data we need at the moment, because this is just the first step, the discovery. We are going to, of course, to address this point in the next months. Of course, it's not that easy. It requires a lot of data because the various channels have different advantages and disadvantages. Gamma has a lot of background, so the spin information is diluted. 4 leptons is cleaner, but it's like low statistics, so it will require a lot of events. So I think it will require a lot of data. How much, I can't tell you at the moment. I don't know if by the end of the year we can already have some indications, or we have to wait for more data later on.
Jeff Brumfield with Nature Magazine, sorry. I know, Professor Higgs, we're not allowed to ask you questions, but can we just ask you to say something, anything? Your name is on the billboard back there. Not all of us work for Reuters. A brief statement would be wonderful. Thank you.
You can ask, but I say this is not the occasion for this discussion. So please, let's continue on the main topic.
Okay, you cannot deny that this was a statement. Okay?
Clear statement.
Fine. The lady over there.
Are you able to explain what other characteristics of the new particle need to be checked to confirm whether it is the Higgs or not?
Well, we've mentioned it a few times. The interesting, at least in the context of the Standard Model, we know everything. We knew everything in advance about the Higgs except its mass, in some sense. So now we're narrowing in on the mass, and so there are many things that are very strictly predicted. What its decay modes are, what its production modes are, and we'll chase all of those things down. Its spin, I presented some things already in the seminar looking at ZZ events and the final state leptons, what were their angular distributions. And we see that there's some consistency with what you'd expect from the Standard Model Higgs. We will try to do all of these things. We'll try to understand whether the spin is 0 or 2, whether it's 0 plus or 0 minus. In terms of parity, there are a whole array of properties that we will test. Some of these we'll get some inkling of by the end of this year, combining data, I think. I don't want to stretch too far, but we've done some projections that look like we can get some of these things, roughly speaking. But then when we come back at higher energy and run with very high luminosity, with lots more data, we'll start really honing in on all of these properties very well.
Now I had the lady here and then the lady in the fourth row.
Can you explain why studying the Higgs boson and not something else could give us a clue on dark matter?
I think that, in order to have a clue on dark matter, we have to look beyond the Higgs boson. So the Higgs boson can give us perhaps some clue in dark matter if we discover that there is a mechanism or there is a theory like supersymmetry that allows the Higgs boson to be so light. Because in the Standard Model, the Higgs boson is being a particle of a new generation, as we said. A boson with spin 0 has some difficulties to be so light, and so needs something that keeps it at the mass that it has. So this something can be supersymmetry, and if it is supersymmetry, we know the supersymmetry has good candidate in its spectrum of particles for dark matter. There are other theories, so I think the Higgs boson may give us some indication, but at the same time, looking for dark matter is a more general question that we are addressing by looking for physics beyond the Standard Model.
Yeah, we're looking directly for these other things for sure. So far, we've come up empty-handed, and that's pushing us to more and more difficult searches. But what I was saying before, and you have to keep in mind, is that these particles are not isolated. They talk to each other. Their properties are interwoven within certain frameworks. And so if this boson that we see turns out to have properties that are quite discrepant from the Standard Model, this is actually also a very big clue about constraining other models that are out there. So that's what I was referring to before. But of course, if we can find other particles directly, that's our preference. And that's what we're trying to do, very vigorously.
Yes.
Elena Dusi, La Repubblica. Are you planning to build a new collider here at CERN? And will these findings be of any guidance for that? Thank you.
Well, I think the management of CERN would be a bad management if we wouldn't have some possibilities in our drawer. But I think it's really premature to discuss this because at the moment the LHC is our flagship, our highest priority, and we have a program for this flagship which I guess goes on for 20 years. But on the second part of the question, yes, of course, any discovery gives you some guidance in what directions you should go, or it also gives you guidance in which directions you should not go. That is true for theorists and for experimentalists. So yes, we have something in the drawer, but we have to wait, we have to see. And I think we first have to get the LHC running at its design energy in the year 2015.
I'm not going to identify myself this time because I have a silly question for you. We journalists, in trying to tell this story over the months and years that it's been running, have found all kinds of metaphors to describe what's going on. Metaphors are incredibly useful and important for this story because it's so difficult for people to understand. But I wondered if I could ask you what your favourite metaphor is, the one you think is a real corker, and your least favourite. And perhaps you could also comment on that dreaded phrase, the God particle. Now, we all know you hate it, but, you know, the fact is it has captured the imagination of the general public, and it does kind of describe what's going on in a way. So your comments, please. Favourite metaphor, least favourite, and what do you think about the God particle thing?
He says men first, so Joe?
I don't know that I have metaphors exactly, but as I said before, the interesting thing about this particle is different than any other. It has a different place. It actually has a relationship to the state of the universe. Okay, and so it's very profound, and that's somewhat more how I view it as in terms of, if you were to connect it to this famous saying of the God particle, it actually embodies the substance to all these other particles that exist, which by rules of the field theories that we live with up to now, these are gauge field theories, all force carriers should be massless. And this was the trick. Somewhere we had to figure out how to get around that. And that was to actually interpret the universe as being in a special state that's represented by this electroweak symmetry breaking. That's not a very good metaphor for you, I'm afraid, but that's how I think about it. I mean,
well, on the question of the metaphor, I just checked. I can tell you the podium is metaphorless. We can't give you any. Okay, I'm sorry. We have a question from Melbourne, I heard. Can I take the question from Melbourne first, and then I come back to you?
Okay, this is a question from the press conference that's happening in parallel in Melbourne. The discovery of the Higgs has been hailed as completing the standard model. What happened to the graviton?
Oh, I think I have a research director.
I mean, gravity is not included in what we call the standard model, and is one probably that there are very deep implications in that. Gravity might enter, is one of the things that might enter very strongly into what we are seeing into the LHC, if we discover that the easy way, just to get away with a number of problems, is not there. Because it's clear that now our comprehension of the world is putting gravity, and the fact that force of gravity is so small compared to all the rest, aside the rest that we are dealing on the same type of scale. The fact that all these scales, somehow they have just to interact, is one of the big things open for us, and tells us that we are at the beginning. This model, as Fabiola was saying before, is not complete, and is remarkably powerful, but it's not complete. So we are at the beginning.
Now the lady in the back row.
Yeah. Hello, I am Isabel Sacco with the Spanish News Agency. I would like to clarify one thing, and then I have a second question. For clarifying, is about the question of time. You have spoken about many deadlines for several things because you don't know exactly what you have found. So for the question of if we will know until the end of this year if you have found the Higgs boson, you will be sure if it is or if it is not. Is it right for the end of this year? With the data you will collect. And I have a second question on
but the answer.
Oh, yes.
The answer on the first question is no. We cannot confirm things until the end of the year. That's not possible. I mean, both said it. It really takes time to pin down the fine details of this new particle.
Follow up on that, because you said some months ago when the accelerator began to work, you said that with the amount of data you will collect until the end of the year, so 15 femtobarns, you will be able to say something about that.
Yes, but that we did. We delivered. We delivered a little bit too early. I said last year, we will make a discovery. Done. I said, we will either exclude the existence of the standard model Higgs boson, the existence of the standard model Higgs boson. We have not excluded it. Or we will discover the existence of a Higgs boson. But there, if you read, then you can see I did not use the word standard model Higgs boson. Because in order to pin it down, it needs time. This is a boson, and therefore we can call it a Higgs boson, but we can only call it a Higgs boson and not the Higgs boson. That's the difference.
My second question, excuse me, but on the question of budget, I know that in the conference room, there were a lot of ambassadors from countries members of CERN. So at what point did the choice to present these results here and not in the Melbourne conference was also driven by the fact that you want to show results to countries, many of them suffering crisis, and to show them that they have to invest, they should continue to invest in CERN?
I think there are several reasons. One reason is that usually big laboratories present their main results, which they will present at the large conferences, at their laboratories before the conference. Yeah? So that's a normal thing, and this is what we did. Of course, it is also a courtesy to our many, many years supporting funding agencies to have it here, but it's also a courtesy towards our staff who have worked very, very much in order to be at that point where we are now. Unfortunately, the lecture hall is much too small to have a courtesy to all of the staff, but at least we could get a few of the staff members into the lecture hall. But I think it's quite obvious that there is a sort of right for those who have invested a lot of resources, human and money and also brains, who have invested a lot of resources into such a big laboratory that they hear the results at this place. And actually, it fits very well with, it was fitting very well with the Melbourne conference. I was in contact with the Melbourne organizers, and they found it a very good idea to have this video link and to have it as a curtain raiser to the conference. So this is why we have chosen also today to do it. Okay, one more, but then I need to wrap up, I think.
Thank you. My name is Hiro Maegawa. I'm an Asahi Shimbun, Japanese newspaper journalist based in Geneva. At this time of celebration, I'm coming from a scientific loving country. I really have some hesitation to ask the questions, but I really have to ask about the budget. Because at the time of this crisis, the European countries are struggling, and look at the world economy after Lehman shock. And because I'm based in Geneva, a lot of international organizations are very well underfunded. And could you explain why this huge project, by the way, I share your dreams, with you, but could you explain why the world needs to invest in this project, and why this has a priority over other global issues like combating poverty or investing in a vaccine that could help millions of people? Thank you.
I guess that's a question to me. Well, first of all, I don't think you should neglect other things. You have to find the right balance to do things, yeah? And one of the, to my mind, most important balance is to balance science in the sense that you support fundamental science and applied science. To me, there's only one science, and there's a whole gray area, so it ranges from absolutely fundamental to absolutely applied. But you have to keep in mind there's a virtuous circle. You have fundamental science, which drives innovation, which drives applied science, which drives innovation, and which drives application. And if you break this virtuous circle, you break something for mankind. So you have to be very careful not to break that circle somewhere. Secondly, in a more blunt statement, if there's no fundamental science or basic science, then you lose the basis for applied science. And you should look around how many things came out of the basic, of the blue sky science compared to the applied science. You have to get the right balance. If you have one sack of corn, do you eat it or do you plant it? In both cases, you are going to starve or to die. You have to find the balance. Part of it you eat and part of it you plant. Yeah? And this balance has to be found. And I'm really proud of our countries here who support CERN in such a way that we can do our basic science, but not neglecting applied science. And you should also see what comes out of this science. In addition, 23 years now ago, the World Wide Web was born here. And this has changed the world dramatically. Yeah? It was born because we needed it, because we were doing our science. So if you take all this together, I think there's a lot of justification once you find the right balance. But the right balance cannot mean that you either suppress fundamental or that you suppress applied science.
Are you reaching out to the emerging economy? Emerging countries?
Oh, sure. How much time do you have? I can give you now a talk. You see, we have 100 nationalities working here. 100 nationalities. We have collaboration agreements with, now here I missed the number, I think it is 45 or so. So we have 20 member states plus associate members plus collaboration agreements with 45 nations. And these nations are not only coming from the already economically developed countries, they are coming also from the emerging countries. A lot with Latin America, a lot in Asia, and also we are starting in Africa. Now, one of the main things we are doing now is also education. Yeah? Education for students, for pupils, and also for teachers. And there we are trying to reach out more and more all over the world in all countries. Because this is, to my mind, the way to overcome poverty. So we reach out, and I think that shows more and more success, and I have a lot of requests from many, many different countries to join into CERN for the educational program. I think James can wrap up.
I think so. Well, thank you all. Thank you for your attention. Thanks to everybody on the panel. If I could just ask you all to remain seated just for a few minutes whilst we allow our guests to leave the room. After the press conference, I know you'll all want one-on-one interviews. Look for people with orange armbands like me and ask us, and we'll do our best to set them up. As you know, Peter Higgs is not giving any interviews after this apart from one pooled interview. So don't ask, please. And I think that's about it. Thank you very much. A group picture of the four? We can ask the question. Would you mind one group photograph of the four of you before you leave? Would that be okay? Then you can take one picture and then go. But everybody else, please remain seated. Oh, why don't you go behind the podium? Why don't you go behind the podium? We take a picture of you there. Yeah. On the place there. Rob, we'll put them behind here with you. Yeah. Oh, if you go behind. Yeah. Thank you. You should grab Francois after this. Yeah. He's going to be there.
It's quite difficult.
Yeah.
These guys, it helps.
Yeah. It's a group photo.
Today is also a special day. Because we hear two presentations from the two experiments, Atlas and CMS, on their update on a search for a certain particle.
I will give the status of the CMS Higgs search. The standard model is shown here. This is what we know. These are the particles making up the standard model that we've known and seen up till now. But there's one piece that's missing, and that's what we call the Higgs. It's very interesting. It's pretty much in agreement with the standard model at 95% confidence level. Standard model's here. This is what we're measuring. So it's a bit off, but again, we need more data. We've seen this. We calculate this. And we conclude by saying that we have observed a new boson with a mass of 125.3 plus or minus 0.6 GeV at 4.9 standard deviations. Thank you.
Atlas is very pleased to present here today updated results on standard model Higgs searches based on up to 10.7 inverse femtobarn of data recorded in 2011 and 2012. And it's a big honor and a big emotion for me to represent this fantastic collaboration at this occasion. So, quantification of the excess. This slide shows, again, the usual p-value as a function of mass, and also the significance now as a function of mass. This distribution is extremely clean, except one big spike here, in this region here. So, zooming in this region. Thank you.
I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that it's happened in my lifetime. It's taken...
We have exciting news. We are homing in to the famous Higgs boson, a particle which we are looking for since decades. And we are now coming closer and closer. We have observed a new particle, which looks like a boson. But frankly speaking, we don't know yet. Is it the standard model Higgs boson? Or is it another exotic, more exotic Higgs boson? In order to distinguish these possibilities, we need many more years of data taking, many more years of patience until we are there.
Ouais, les jaunes, bon, les jaunes à l'intérieur, c'est les traces.
One of the possible things that we'll see at the LHC are signs of a new particle called the Higgs particle. Now, if this exists, it could explain why some other particles are heavy and some of them are light.
We've observed a new particle. We see that it decays to 2 photons, for example, which tells us it's a boson. It's a particle with integer spin, and we know its mass is roughly 130 times the mass of the proton. And this is very significant. This is the most massive such particle that exists, if we confirm all of this, which I think we will. And that is very, very significant. This is something that may, in the end, be one of the biggest discoveries or observations of any new phenomena that we've had in our field in the last 30 or 40 years, going way, way back to the discovery of quarks, for example. We're very excited. I'm extremely tired at the moment, so I may not appear to be as excited as I really am, but the significance of this observation could be very, very great. It could be ultimately seen that its properties are very consistent with the Standard Model Higgs, or we may find out that some of its properties don't exactly match the expectations for the Standard Model Higgs. And if that's the case, then we have something really quite profound here. And it could be a gateway, if you like, to the next phase of exploring the deepest parts of the fabric of our universe, which is pretty profound when you think about it.
Today's results is very important for Atlas. Is a big award for more than 20 years of efforts by the international community. Atlas consists of 3,000 physicists from all over the world. Today we announce a preliminary but very important result. based on the data that we have recorded last year and also in the first months of 2012, and thanks to the outstanding performance of the LHC accelerator and of the experiment, we have been able to arrive at an observation much faster than expected. This observation is a signal at the level of 5 sigma, so it's a significant signal, which could be due to the production and decay of the famous Higgs boson. Now, results are preliminary and will be firmed up in the next few weeks until we publish them. After the publication, of course, this is not the end of the story. It's the beginning. We have to study in details the properties of this signal to understand its nature, to understand if it is really the standard model Higgs or another Higgs boson or something else. So in some sense, this result represents the end of something and the beginning of a new era.
I'm really happy, and now we also know which direction to go for the future. But first of all, as I said, it's the beginning of a long journey to investigate all the properties of this interesting particle, because if it has a spin zero, if it is a scalar, it would be the first fundamental scalar which we ever have discovered. We have not yet ever seen a fundamental scalar, and that could give a lot of hints on other questions beyond the standard model, and I think this is very, very important, and this is why everybody is not only excited about the discovery, everybody is also excited about the prospects this discovery opens for us, for the field, and for physics in general.